from here to here is L over 2. Hey, Eugene, you say L, you write X. Seriously, what's wrong with you today? Okay, so that is straightforward, evenly distributed load. Then if we have a gradient distributed load, right? So now we have, again, point A, point B, okay? And then from here to here is L, right? We have now a gradient distributed load. Right? And at this point is omega Newton per meter. So when we draw our free body diagram to determine what is point A and point B, we know that our equivalent load, right? You guys know this already. Our equivalent load over here is half base or height times base, right? And we also know that the distance from here to here, right, is 2L over 3, and the distance from here to here, oh, sorry, wrong color. I do apologize. Come on, come on. We know that the distance from here to here is 2L over 3, and the distance from here to here is L over 3, right? That is straightforward. Now, what if, so far so good, yes? Right? What if now okay, what if now still same thing, point A, point B, and this is now a function distributed load. And then we have this sort of profile. And our function, this is omega as a function of x. And now this is our distributed load. Right? Now the question is this now. Can someone tell me the equivalent load is easy to find? Okay. Or not easy, but what is the equivalent load? And what is this distance? When we want to find AY and BY. Or what is this distance? Anyone? We don't know, right? We don't know where is the equivalent. Not just the equivalent load. Where the equivalent load is applying that distance, we also don't know. If we don't know, how are we going to find the reaction at A, and how are we going to find the reaction at where? At B. Okay? And when this is the case, okay, we have to apply the integration method. Okay? We have to apply the integration method. So I'm not going to go too much into deriving it. Okay. All I can say is this. Okay. We're going to apply. So the first thing we have to write is dv over dx is equal minus omega as a function of x. Okay. Let's do this first. Okay. dv over dx is equal to a function of minus omega x. So what is omega x? Omega x you see over here, and the omega x you see over there have the same function. Okay. Then after this, we are going to integrate once. Okay. You will have v as a function of x. You integrate minus or integrate minus omega as a function of x dx plus by what? C1. Okay. And this whole thing is also equal to dm by dx. So this function over here, as you can see, the first one, right? It is your what? Your shear force as a function of x already. And the shear force as a function of x is equal to dm by dx. Then you integrate again. You have m as a function of x. You integrate twice. Okay. Now you get your what? Moment. So this is your shear force equation. And this is your bending moment equation. Okay. It's that simple. Okay. Now, I'm not able to convince how simple it is until we do an example. Okay. I'm going to stop here for now. Okay. Hold on. Don't go anywhere.
Sir,